Okay, so now we're recording. Yeah, this is worksheet 14 that was just uploaded 10 minutes ago or so. In the meantime, so why don't we work on some of this? In the meantime, let's see. There were a few homework questions we wanted to go over. Can you type those into the chat, which ones those were? And then some administration. I'll put down here. Administration. Okay, so homework questions were 6.2, number 25, and 6.3, number 24. Okay. Trivia. So one, let's see, worksheet 13, answers, not yet published. I'll probably try to write those and put them out on Friday. Actually, maybe just by a show of hands. I think there's like some sort of emoji you can do. Do people actually look at the worksheets and or the solutions? If you do, just give me some notification in some way. Okay, so a good amount of you. 1, 2, 3, 4, 5, 6. Okay, so I'll keep writing some worksheets then, and I'll keep putting up solutions. Some other homework questions were 5.5, numbers 17 and 25, 6.2, number 23D. Okay. Okay, yeah, so administration, worksheet 13 answers not yet published. I'll try to do that by Friday, hopefully, or maybe even Thursday. 2, there's a quiz today. It's a little different than normal. It is timed. So as soon as you open the quiz, you'll have 30 minutes to complete it. It's all on Gradescope. And you have to upload something to Gradescope, as well as answer some true-false questions. So the important thing is that it's timed, so don't open it assuming you have 24 hours. That could be bad. What else? 3, I mean, assuming it all goes well today with the quiz and the time quiz, it's very likely that we'll have a midterm in the same format. So the midterm, probably the same format. Depending on just how well it goes. Let's see what else. What content is the quiz going to cover? The content should be nothing of this week, so all of 2 weeks ago. So the content of the quiz will be so orthogonal projections could be on it. Orthogonal complements, how to find a basis for orthogonal complement. What else? No, I mean, nothing about Gram-Schmidt, nothing about least squares. Those are mainly the 2 things that'll be covered. Let's see what else. I don't think anything about diagonalizability or anything. So yeah, that was all that was covered on Thursday of last week and Tuesday of last week. Complex eigenvalues, was that on Tuesday of 2 weeks ago? I do not know. I mean, I can check the website. Yeah, okay, so complex eigenvalues were covered on Tuesday. Then yeah, those technically could be covered on the quiz. It should be whatever it was on Tuesday and Thursday of 2 weeks ago. But I mean, I'll say that like, or the orthogonal complements and orthogonal projections and just anything orthogonality wise is probably going to be stressed more on the quiz. Okay. So why don't we go over these warm-up questions, and then since there's enough homework questions, we might as well just go over some of these homework questions, and then we'll do some stuff on the worksheet. So yeah, let's go over these warm-up questions. What do we think? Does anyone want to wager some answers for 1, 2, or 3? What do we think? True, false, true, false? Feel free to type in the chat. Or unmute yourself. You're always welcome to unmute yourself. Okay, well, I'll give you the answer to number 1 then. Warm-up number 1. For square matrix A, column space of A is orthogonal to null space of A transpose. This is true. Right? Because what does this mean? The column space of A, those are the space spanned by the columns of A. So if A, maybe here's A, and it's got some columns, right? And now let's look at the null space of A transpose. So here's A transpose. So that means in its transpose, these columns A1 through AN are now rows. Right? And the null space of A transpose is all the vectors X such that A transpose X equals 0. Right? So if you just look at this over here, if you look at this on the right-hand side, what we're saying is that each row, A1 transpose X equals 0, and A2 transpose X equals 0, AN transpose X equals 0. So this is exactly saying that X is orthogonal to A1 through AN. Right, which is saying that anything in the null space of A transpose is orthogonal to all the columns of A. So in particular, these are 2 orthogonal complements. These are orthogonal complements of each other. Okay, and a way to visualize that is you have like kind of a big space, which is your column space. And an orthogonal complement is what you kind of envision as just sticking out normal to this space. So the null space will be orthogonal to this in some way. So they kind of, it's another space that's perpendicular to the column space. So this is maybe the null space of A transpose. And they should be orthogonal to each other. And this is just inside some big Rn. Okay, number 2. The orthogonal projection of Y onto W can depend on the orthogonal basis of W used. What do we think, true or false? Any guesses? False. Correct. It does not depend on the orthogonal basis of W used. Right? The orthogonal basis, the orthogonal projection, is just uniquely defined. Right? It doesn't depend on how you compute it. It's just always going to be the same thing. The calculations may look different when you compute it, but you're always going to get the same thing. Because you always have some space W, and you always have some V. Can people not hear me? Raise your hand if you cannot hear me. Okay. Sounds like most people can hear. If you can't, maybe log or exit and log back in. Here's W, here's V. The orthogonal projection is always just uniquely defined. Okay, and the last one, a space W has only finite many orthonormal bases. This is false. Okay, a space W has infinitely many bases and infinitely many orthonormal bases because we can always take a basis and make it orthonormal by using Gram-Schmidt. Okay, great. Let's maybe, let's spend a few minutes going over some of these questions, and then we'll talk about Gram-Schmidt. Okay, so I unfortunately don't have the book in front of me. So someone will have to read off some of these questions. So maybe we can work on the first one. In the meantime, someone can write the questions in the chat or tell me in some way. So I'm going to erase some of this. What is 6.2, number 25? You can, someone could tell me. Or any of the questions, we don't have to go in order. Prove theorem 7 from 6.2. Okay, what is theorem 7? So yeah, sorry, I don't have the book. Maybe, or maybe someone could, I mean, if someone has a PDF, an online PDF, then they can share their screen briefly. Maybe you could raise your hand if you have that. Yeah, 5.5, number 3. Sure, what's number 3? I mean, if someone has maybe the fastest way to do this is if someone has a PDF of the book, we can have you share your screen, and then I can just like take a picture of the problems really quickly, and then I have something to look at. Or maybe just send me a link.
I have a picture of it.
To the online thing. I can try Googling quickly for a PDF.
You can.
That
link just sends you to the picture of it.
Okay, great. That's perfect. Okay, so prove theorem 7. And Hannah can also, okay. So we didn't, so, okay, 6.2, yeah, I see, I have to make you a host to share screen. So 1 second. 6.2, I'm actually gonna say I'm gonna defer this question. Number 20 is number 25. Because it talks about orthogonal matrices, which we haven't talked about in lecture yet. So I think I'm going to talk about this after the first section. So I think at like 11 or so, or maybe after 11, I can talk about orthogonal matrices. But I want to talk about Gram-Schmidt before I do that, since the lecture hasn't talked about these yet. So I will get to them, just not right now, because I don't want to derail the section. So for now, I'm going to delay this question. And is there any other question that talks about orthogonal matrices or orthonormal columns like that? We're just going to delay that till after. So maybe let's do 5.5 number 3, maybe some of the 5.5 questions for now. And then let's see, 5.5 number 3. If that's a basis for each eigenspace in C2. What was the question there? I'm just going to kind of look through all these questions real quick. 3, what else? 5.5, number 17 and 25. Okay, so these have to do with like eigenvalues and eigenvectors. Okay, I might actually delay all of these questions until 11 so that we can talk about 6.3, number 24, so that we can talk about Gram-Schmidt. Well, actually, let's do 6.3, number 24, because that this is about orthogonal complements. Yeah. So you have 6.3. Let's talk about this one. And then the other ones, so 5.5, these are probably all complex eigenvalue stuff. And we'll do this one right now. And then 23D, if that's about orthonormal columns, I'll just delay both of these till after. So we'll delay this as well. Okay, and then we'll talk about this one right now. Okay, so this is, you have W1 through WP. This is an orthogonal basis for W. And you have V1 through VQ, orthogonal basis for W perp. Okay, and then just explain. So one is explain why, if you combine them, it's an orthogonal set. So we just need to explain why every pair of vectors in here is orthogonal to each other. Okay, and so there's 3 different types of pairs. We can pair some W's with each other. We can pair some V's with each other. We can pair a W with a V. Right? And each one we have to see why they're all orthogonal. Right? But the W's are orthogonal because they're an orthogonal basis. The V's are orthogonal because they're an orthogonal basis. And then the W's and the V's are orthogonal with each other because of the fact that they're bases for their orthogonal complements. So we have Wi dot Wj equals 0. That's just because they're orthogonal. We have Vi dot Vj equals 0 because they're orthogonal. And then we have Wi dot Vj equals 0 because Wi is in W and Vj is in W perp. And by definition of W perp, this means it's orthogonal to things in W. Okay, so that's why the first part's true. And then the second part, explain why the set in part A spans Rn. Well, that's really just the orthogonal decomposition theorem. So you want to say why this spans Rn, which means that if you take what that means is if we take any vector in Rn, we can write it as a linear combination of things in W plus something in W perp. So to say that again, if y is in Rn, we need to be able to write y as some linear combination of things in W plus some linear combination of the vectors v1 through vq. So can we write y as something in W plus something in W perp? So this is in W. This is in W perp. So does there always exist this like equation? That's kind of the question, right? And there does, and this does exist, right? This is called the orthogonal projection, right? So this does exist because, so this exists because W is just the orthogonal projection of Y onto W, small w. Right? And then Z just equals Y minus the projection. Right? So you can always write any vector as something in W plus something perpendicular to W. And so that's why this space spans Rn. And then just to finish it off, you have P plus Q vectors. They're orthogonal, which means they're linearly independent, and they span Rn. So together that means they're a basis. Plus span, this implies basis for Rn, which means that that n, which is the dimension of Rn, has to equal the size of this basis, P plus Q, which is the dimension of W plus the dimension of W perp. That's what they're kind of getting at for this question. Yeah. Okay, so we finished this one. These ones are all delayed. So these ones and these ones we're going to delay to after. And then if there are no more questions, let's talk about Gram-Schmidt. So I will save that. Okay. Right, okay. So just kind of going along with the worksheet. Let's just remember, just so we're all on the same page, we have W is a subspace of Rn. V is a vector in Rn. What is the orthogonal projection of V onto W? What is the formula for it? So let's think about this for a second. See if you can try to fill this out without looking at a book. And I'll give you a hint. Maybe we should define some things. Maybe let's let W1 through WD be something for W, be and something for W. So we have W1 through WD. What is this formula? So everyone think about that for about 30 seconds. See if you can fill it out. Maybe by reasoning through something, or maybe by memory, whatever you'd like. Okay. Hopefully you didn't just wait for me to write the answer, but if you did, that's okay. So what is the orthogonal projection of V on the W? So we need to first find W1 through WD, an orthogonal basis for W. This seems to be an orthogonal basis. Yeah. I mean, it really just needs to be an orthogonal spanning set. But if it's orthogonal, then it's automatically linearly independent. And if it spans, then together that means it's a basis. So you take an orthogonal basis for W, and then you project onto each one of these. You take V and you project onto W1, and then you add it to the projection on W2, right? You break it up into each component. And the projection onto each one of these, well, we've done that. That's the projection of a vector onto just a line. It should be V dot W1 for W1 dot W1, the W1 direction. Plus, can you do this for each one of these? Each one of these is the projection of V onto the line spanned by W1. This equals projection that says W1 span W, D, V. And if you ever forget this, I mean, you could try redriving it. You can just say, here's W1. Maybe you have a whole line. It's W1, and you have V, right? So the projection should be this thing. So this is like some constant times W1 should be the orthogonal projection. And then you can just derive it by saying that the difference must be orthogonal to W1. And then you can solve for C. So it's not too hard to rederive, but it's nice to know it. Okay, great. So that's the orthogonal projection. But the question is, and this came up yesterday, what happens when we don't have an orthogonal basis? When we aren't given this? Right? We can't find orthogonal complement or orthogonal projections anymore. Right? We need an orthogonal basis for this formula to work. Which means that we need to have some procedure for finding orthogonal bases. Right? We have a nice procedure for finding normal bases. For example, if you have a basis, if you want to find a basis for a null space or a column space, we know how to do that. You row reduce and you find your pivot columns and your free columns, and depending on which one you're doing, that tells you what your basis is, right? But we don't know how to find an orthogonal basis until now, right? And the way we do that is we do Gram-Schmidt, which means we take a normal basis and then we do one extra step, which is perform Gram-Schmidt to kind of come up, we construct a new basis that is orthogonal. So the answer, perform Gram-Schmidt, named after Gram and Schmidt. Okay, so let's basically just do this by example. So I have a matrix here. You know what? I'm gonna try something different, just to add another page. Okay. Example. Let's find an orthogonal basis for column space of A, where A is this matrix here. Let's see, 1, -1, -1, 1, 1, 2, 1, 4. Okay. So we have a matrix here. It's a 5 by 3 matrix. So we want to find an orthogonal basis for this column space. So just so everyone's on the same page, this column space lives inside R5, right? Because the columns are in R5. And it's at most 3-dimensional because there's 3 columns here. And those 3 columns span the column space. So our column space is at most 3-dimensional. If these are all linearly independent, then it's 3-dimensional. This isn't helpful to Gram-Schmidt, just kind of noting some stuff. So this is probably some 3-dimensional space inside R5. Okay, so let's do Gram-Schmidt. So let's just call these things. Let's call this, well, okay, I want to use the same notation as the book, but I don't have the book, so I'm going to hope this is the same notation. Let's call this x1, x2, and x3. You know what, that's a bad name. Let's call them B1, B2, and B3. They're just some vectors, and we're going to construct V1. We will construct V1, V2, and V3 orthogonal. Well, I mean, maybe this is actually a lie. If B1, B2, and B3 are not linearly independent, then we're only going to construct V1 and V2 orthogonal, because the third one's not going to be orthogonal, it'll just be 0. So, okay, I'll just, maybe what will I say? We will construct an orthogonal spanning set VI that spans column space of A. That way I'm not being incorrect. Okay, and we're gonna do it step by step. The first one is we set V1 equal B1. Right? We're gonna do it step by step, and we're just gonna make sure it's orthogonal at each step. And if we just start with the first vector, it's always orthogonal, because it's a single vector. In the same way that a single vector is linearly independent, a single vector is an orthogonal set. All right, now we're going to construct V2. And you'll notice that the order does change the outcome, right? If I chose B, if I relabel these in a different order, then V1 would be a different vector, and you'd get a different orthogonal basis, but that's okay. I mean, usually we don't care exactly what orthogonal basis we get. We just want any old orthogonal basis. So V2, we want it to be B2 because we want it to span the same thing, but B1 and B2 are not necessarily orthogonal. And so we need to subtract off the part that, that makes it not orthogonal to B1. So let's draw a picture. Here's B1, say. Here's B2. These are not orthogonal as I've drawn them. But if we want something, if you can subtract off the part of B2 in the direction of B1, subtract off this orthogonal projection, let's be precise, then we get something that is orthogonal and the space is the same. Projection onto the span B1. Then now the difference will be orthogonal to B1 and their span's going to be the same. So we're going to subtract off the projection onto the span B1, B2. Okay. So it's B2. Let's put in some numbers. It's 2, 1, 4, -4, 2. It's very easy to make a mistake with Gram-Schmidt because there's just so many dot products we're taking that you just want to take it slowly. You don't want to miscopy anything. So just make sure I didn't miscopy anything. Okay, and then the projection of B2 into B1 is B2 dot B1. Maybe just remind ourselves. This is B2 dot B1 over B1 dot B1, B1. You know, so a good way might just be to like normalize everything so you don't have to do these dot products on the bottom, but it's whatever. So B2 dot B1, we take the dot product, we get 2 minus 1 is 8 minus 7, 6, or no? Minus 5. And then over 5. Okay, and that just gives us 2 plus 5 is 7. Or sorry, erase. This is a 1. One minus 1 is 0. 4 minus 1 is 3. Minus 4 plus 1 is minus 3. 2 plus 1 is 3. All right. Let me know if I made a mistake anywhere. Okay, and maybe we should just quickly check that these two are in fact orthogonal. It's not too hard to check. So 3 minus 3 is 0, and then minus 3 is, yeah. So these two vectors are indeed orthogonal, B1 and, or V1 and V2. So just maybe a good check. V1 and V2 are orthogonal. It's very easy to check orthogonality. Okay, and now we're on V3. I'm gonna have to erase something here. I'll erase this. And I'll write V3 over here. Right, so we want it to be B3, right? But now we're gonna, again, subtract off the part that makes it not orthogonal with B1 and B2. So we want to subtract off its projection onto the span of B1 and B2. Right, so we have B1, B2, they form some space. And B3 is maybe not orthogonal to it. So we want to subtract off its orthogonal projection. So let's just write something. So here's V1 and V2. They actually are orthogonal when they span the space. Right? And B3, we're going to subtract off its orthogonal projection. And so this is going to be our V3. And now we're going to get 3 orthogonal vectors. So it's going to be B3. So the projection of B3 onto the span of B1 and B2, we just have a formula for that. That was on the last slide. Right? We take an orthogonal basis for this span, which we already have now. It's V1 and V2. And we project onto each one of those. So it's going to be B3.V1 over V1.V1, V1, plus B3.V2 over V2.V2, V2. So you'll notice that we're using this V1 here and this V2 here, right? Not B1 and B2, because we need to project onto the span of B1 and B2, and B1 and B2 are not orthogonal. And so we can't use those to project, we need to use V1 and V2. So question, would it be different if we project on the span of V1 and V2? Yeah, so exactly what I just said. It would be the same because the span of V1 and V2 are the same as the span of B1 and B2. Let me write that out. Span of V1 and V2 is equal to the span of B1, B2. Right? Just because that's what we're doing with Gram-Schmidt. We're making sure the spans are exactly the same, but just that the added benefit that V1 and V2 are orthogonal. Wow, I realize now I shouldn't have said B1 and B2 and B3. That's a bad choice because B's and V's sound alike, but it's too late now. So, I mean, you can change this to V1 and V2 if you want, right? In the end, you're doing the same calculation, right? You need V1 and V2 because the spans are the same. So however you'd like to write it to keep everything straight is fine with me, as long as you're taking the correct dot products. All right, and now we can just simplify. Yeah, exactly. So just to clarify, even though the spans of the B's is the same as the spans of the V's, to correctly do the orthogonal projection here, you need to project onto an orthogonal basis, and that's the V's. V. So you need to project with the V1 and V2. So maybe so we don't get confused, it's even better just to, instead of writing span of B1 and B2, maybe it's just better to write V1, V2. Maybe there should be V1 here, just so we don't get confused. So maybe I can write V1. Both are correct because the spans are the same. How do we prove that the spans are the same? Well, yeah, 2 questions here. So the first one, how do we know the spans are the same? Well, what have we done? We've taken B1, is a little bit of a digression here. Can't draw lines. We want to compare the span of B1 and B2 with the span of B1 and, so erase, undo, V1 and V2. Let's just plug in what V1 and V2 are. That span of B1, that's V1 equals B1. And then V2 is just B2 minus just some multiple of B2, right? This projection is just some multiple of B2, or I'm sorry, B1. So it's B2 minus just some multiple. I don't know, I'll say CB1. Right, because that's what this is. This is your C. That's your C here. So why are these spans the same? Just because we're only subtracting off a multiple of some other vector in the span, I guess. Maybe what's another way to say this? I mean, I guess you could think about this as some row operation. Let's not go into that, actually. But maybe we can just look at this and see why the spans are the same. Right, if we want some, if we have some x, that's just some linear combination of b's, then we get the same linear combination of these vectors, just altered a little bit. We'd have lambda plus c b1 plus lambda 2 or probably a lambda 2 here. Yeah, so they're going to span the same thing. We're just subtracting off a multiple of some vector. I'll let you ruminate on that for a little bit. And then the second question is, could you explain why we can only project onto orthogonal bases? Yeah, you need orthogonal bases. If they weren't orthogonal, then I mean, it really, so I'm going to do this. I'm going to answer, I don't want to erase anything here, so I'm going to answer on a separate page. It's really just, actually, I think I might have saved it. Oh yeah. It's really just down to this fact. Right, so if, or maybe it's down to the fact of two things. If we have a basis, if B1 and B2 are a basis, let's say we have a two-dimensional space for some W, but they're not, let's say they're not orthogonal. Right, then let's say we want to try to write a vector as some sum of B1 and B2. Right, if we want to figure out, we want to solve for C1 and C2. Right, if they're not orthogonal, B1 and B2, then to solve for this linear combination, you need to set up some linear system. Right, you need to form a matrix whose columns are B1 and B2, and let's say and Y is on the other side. And you need to solve for C1 and C2. But if they are orthogonal, then you don't need to solve that linear system, right? Because you can solve for each coefficient immediately, right? If you dot this with B1, then you would get C1 B1 dot B1 plus C2 B2 dot B1. And if they were orthogonal, let's see this. If they were orthogonal, then this would be 0. And so you just get that C1 equals y dot B1 over B1 dot B1, right? But if they're not orthogonal, then none of this is true. If they're not orthogonal, then none of this is true. And so just the orthogonal projection just doesn't work anymore, right? You don't get these, you can't solve for these coefficients in the same way. Dot product there. Okay, so why don't I finish the calculation and then we can talk about it a little more. So I'm going to finish this. Okay, and we just plug it in. Minus, and then B3.V1, 5 plus 4, 9, plus 3, 12, plus 8, 20, I think, over 5. B3.V2, 15 minus 9 is 6, minus 21 is minus 15, plus 3 is minus 12, I think, over 9 times 4 is 36. Okay, hopefully I got that right. And then you just get something. 5 minus 4 is 1, 2, 0, 1 plus 1 is 2, 2, negative 2. Is that right? I think there might be a negative sign missing. Okay, but in any case, this is Gram-Schmidt. And we should just check, yeah, because I think negative 6. Oh no, that's fine. That's fine. And we can just check really quickly that these two are orthogonal. Just do a quick check. V3, V1 are orthogonal, and V3 and V2 are orthogonal. And you can just do dot products really quickly to check. Yeah, so are there any questions that we have about how to do Gram-Schmidt? It's very easy to make mistakes. It's advised you do it slowly. I'm gonna take let's take a minute break or so, and then we can go over some of those homework questions that we had. And then if we want, we can do another example for Gram-Schmidt. I was gonna do least squares on Friday because it's just too much to pack into one day. Okay. Let's look at some of these. 6.2, number 25, and then 23D, and then 5.5. Okay. The setup is U as oh, I should say that. Oh yeah, we found an orthogonal basis. It's a very easy points that can be taken off if you read the problem incorrectly. Is if we ask you for an orthonormal basis. If this was orthonormal instead. This was orthonormal. Then after Gram-Schmidt, you'd have to normalize all of these. So then you'd want to divide by the norm here. You want to divide by 6. And divide by 4 times 4 is 4. Just to make it a unit length. So it's an easy like 1-point deduction if you forget to normalize if you ask for an orthonormal basis. Okay. We want to prove theorem 7, which is okay, so this actually isn't too bad once you just reformulate what this means, right? Because all of them are essentially the same proof. These proofs are all the same. For example, I mean, C is exactly the same as B, right? You can deduce C from B because like you have this equality, right? So if one's 0, then the other is 0, and so forth. And C or an A is just the same as B if you just set Y equal to X. Then you get the norm of X squared, and you get the norm of UX squared, and so you get this equality. So they're really just the same thing written in various ways. And so we just really need to prove any one of them. For example, let's look at B. Let's prove this. And let's just write out what this means. So UX, let's write it, and instead of a dot product, let's write it as a matrix multiplication. UX dot UY equals, so it's the transpose of this times this. When you transpose, you have to reverse the order. And now we kind of, let's just break this apart. This is, and we'll see what's going on here. So U is m by n. So let's do something like this to make sure it's not square. You have some column as orthonormal columns. So let's say V1, Vn. And the transpose means these columns become rows. So the question is, what happens when we multiply this? What matrix do we get? Exactly, we get the identity matrix, right? Because the first entry here is v1 dot v1. That's how you compute this first entry. You take this first row and this first column, you overlay them on top, and you multiply them component-wise and add them up. That's just taking the dot product. So v1 dot v1, and since they're orthonormal, v1 dot v1 is just 1. This is v1 dot v1. What about this second entry? Right, that would be v2 dot v1, but those are, since they're orthogonal in particular, this is 0. And all of these are going to be 0, because this is v2 dot v1. And all of these are going to be 0. And the only non-zero entries are these diagonal entries, because that's the dot product of each vector with itself. And so this is the identity matrix, which means U transpose U here is the identity matrix. And so you can just get rid of it. It's just the identity matrix. And this is just x dot y. So we just showed that ux dot ui equals x dot y. We just proved part B. And like I said, part B implies the rest. Does this only imply when it's orthonormal? Yes. So if it's not orthonormal, then these ones are not going to be ones. They're going to be whatever the dot product is. So if they're just orthogonal, then instead of 1 here, for example, you're going to get some number. It's going to be whatever vn dot vn is. It might not be 1. So you just get a diagonal matrix. So you do need them to be orthonormal, need this. Not just orthogonal, you need it to be orthonormal. All right, let's talk about 20, that was 25. Okay, we did 25. We did this one, 23D. Yeah, so this is like 23D. We're getting ahead of lecture at this point. It's kind of weird. The homework's like hasn't really been covered in lecture. If you have a matrix, so 23D is a matrix with orthonormal columns. It's an orthogonal matrix. That's just the definition, or we say definition. We haven't, this is not yet seen in lecture. A square matrix with orthonormal columns is called an orthogonal matrix. For some reason, it's just historically, we don't call it an orthonormal matrix, we call it an orthogonal matrix. It's a unfortunate use, but don't be confused. An orthogonal matrix means the columns are not just orthogonal, but actually they're orthonormal. And it needs to be square. So, right, another way to say this is, usually this is the definition you see, i.e. U is orthogonal. So a matrix we say is orthogonal if U transpose, I'll do U transpose U equals the identity matrix. And U transpose. Sorry, there should be this other thing as well because it needs to be square. There is a key property here. We only say matrices are orthogonal if they're square. So both of them are satisfied, which means, i.e. U inverse is the transpose. This is the upper T. And so 23D just says a matrix with orthonormal columns is an orthogonal matrix, and that's false because it needs to be square. False. You need to be square to be true. Well, yeah. We haven't gone over this in lecture, but so that's why it was maybe a little hard. But we'll probably go over it on Thursday, maybe Tuesday. Okay. And what about 5.5? Is the person who asked about 5.5 still here and wants to see it done? Five, number 17. Okay. You have an invertible matrix P. You're going to find P and C of the form. So you want to find P and C that looks like this. So that A equals P, C, P inverse, and A here is equal to 1, 4, -8, and -2.2. That's just disgusting. It's an 8. Actually, fun fact, this matrix here is an orthogonal matrix, granted that their unit length, if A squared plus B squared equals 1. Right, because if you take the dot product between these two vectors, AB and minus BA, you get 0. So in fact, these columns are orthogonal, and they would be, so this matrix would be orthogonal if the columns are also orthonormal. So we've seen orthogonal matrices before. Okay. So it looks like you just need to diagonalize it, find the eigenvectors and eigenvalues. You probably get complex eigenvectors and eigenvalues. And then you're going to invoke, so you diagonalize, get complex eigenvalues and eigenvectors. And then step 2 is you invoke a theorem, essentially, which says that P equals, tells you what P and C are. Tells you take the real part of your eigenvector and you take the imaginary part of your eigenvector. Remember, they come in complex conjugates, and A equals the real part of your eigenvalue, and B equals the imaginary part of your eigenvalue. I think it's something like that. Question. There will not be any new material, I think, unless we want to go over new material. But I do not plan to go over, I wasn't planning on going over least squares, just because that's a whole nother thing, and I want to take that a little more slowly. But we can do Gram-Schmidt again if you'd like. With complex eigenvalues, are you always guaranteed n basis vectors, where n is its multiplicities, unlike when we are uncertain in Rn? No, you're not always guaranteed. So if I'm reading this correctly, do you mean n eigenvectors that are basis vectors? Yeah, we can do this more slowly. Yeah, so with complex eigenvalues, you're always guaranteed n eigenvalues if you count multiplicity. You always have n eigenvalues. but you still may not be diagonalizable. You still may not have n linearly independent eigenvectors. For example, you could have a single eigenvalue repeated twice, or repeated, n times. Maybe it's complex or not. Well, if it's complex, it'd come in pairs. So, but then that eigenspace could just have like a single eigenvector in it. So let me continue with this. So I'll just write that down. Note with complex eigenvectors. So in the complex setting, you always have n eigenvalues counting multiplicity, just because a polynomial of degree n always has n roots, n complex roots, if you count multiplicity. But you still may not have n linearly independent eigenvectors, right? Because your matrix still may not be diagonalizable, right? Otherwise, every matrix would be diagonalizable if you had n linearly independent eigenvectors. Okay, and to actually do this problem, right, you want to set up the eigenvalues and eigenvectors. So you want to, so you want to do determinant of 1 minus lambda for minus 8 minus 2.2 minus lambda. And this is just kind of annoying, I guess. 1 minus lambda, because you have this negative 2.2. Maybe it's better. Plus 32. Lambda squared plus 2.2 minus 1. Yeah, it's probably just better to plug this into like a computer at this point. Or multiply everything by a common denominator. Yeah, I don't know. Plug into computer. We're not going to give you these numbers on a test. Plug into computer, and you get what do you get for your eigenvalues? Lambda equals something. We'll just plug into a calculator. You get b squared is 1.2 squared minus 4 times 29.8. And then the square root of that. Looks pretty annoying. If I did everything correctly there. Squared. Yeah, don't really feel like solving for lambda here, but you get something, and then whatever you get, you take the real part of that. You get a plus or minus bi. A is this real part, b is the imaginary part, and then you plug this back into here, and you solve your eigenvectors. With numbers like this, I mean, I would just use a computer, to be honest. You can just go to like www.wolframalpha.com and plug it in. Okay, what are we looking at? 25. think we talked about that at some point. 3. Yeah, are there any other questions people have? What is the point of doing this? You mean writing it as PCP inverse? Well, with diagonalizing a matrix, if everything is real, if all your eigenvalues are real, then it gives you some intuition about what the linear transformation is. It's some change of basis, and then you scale the vectors, and then you change it back. But with complex eigenvalues, it's weird, right? Because what does it mean to multiply by the complex number I? Right? If you're linear, in the real world, real quotes, your linear transformations should really be from real vector spaces to real vector spaces. So what does it mean to have this complex number floating around as some eigenvalue? What does it mean for an eigenvalue to be I, for example? And so what this is doing is kind of giving you meaning about that. Complex eigenvalue, say I, for example. What does it mean to scale by I? Well, it actually means a rotation is what this means. And what we're doing here is we're kind of writing out what this complex eigenvalue means with real numbers. So this matrix here, like I said, this is actually an orthogonal matrix. If a squared plus b squared is 1. So really what this is saying is that instead of scaling, you replace this with an orthogonal matrix. And I guess there's another further question, which is what does an orthogonal matrix really mean? And an orthogonal matrix is really geometrically is a rotation or a reflection. So what we're doing here, we're running it as PCP inverses. We're really rewriting this complex eigenvalue I, scaling by I. We're rewriting it as, in the real world, it corresponds to some rotation or reflection. And this is a rotation matrix. So the rotation matrices that we saw were cosine theta minus sine theta, cosine theta. So if a squared plus b squared equals 1, then this is exactly the same as there's some theta you can put in here to get this matrix, and so that's how we're interpreting it. That's kind of, I don't know if it's beyond the scope of this course, but it's the geometric intuition of this course, of orthogonal matrices, which I don't know how much we're going to talk about. Okay, so I'm going to clear this. And I'll say, that's all for now, but you're welcome to sit around and ask questions. Sure, you're welcome to ask about number 3 with your voice.
Okay, I wanted to ask just a general question, I guess, but number 3 was just a good example.
Mm-hmm.
So number 3 is also asking for the complex eigenvalues.
Mm-hmm. Yeah.
And then looking for the basis.
Okay.
So I understand how to find the eigenvalues. So once you get there, so the eigenvalues are, I think, 2 plus or minus 3i.
Minus 4 lambda plus 3 10. Yeah, you get 16 minus 49 over 2. Did I do that wrong? So what'd you get? 2 plus or minus something?
I got 2 plus or minus 3i. And then,
Oh,
so
minus.
once I get into looking for the eigenspace, is that what it's called?
Yeah, the eigenspace.
Yeah, so once we get there, so if this wasn't a complex value, or like the eigenvalues were real, then you would like row reduce and you would like solve for the null space, right?
Yes. You could do the same thing here.
Right. So when I looked at the answers, how would you solve, I guess, for the null space?
Okay, yeah, let's do one of them. Let's do lambda equals 2 plus 3i. So I can plug in lambda here. I get 1 minus 2 plus 3i, 5 minus 2, 3 minus 2 plus 3i. Okay, so I get negative 1 minus 3i, 5, negative 2, 1 minus 3i. Yeah. Okay, and we want to solve for the null space. So you could do exactly the same thing you normally do. So you could take this first number as your pivot, and then you could use that to, I mean, you could, if you want, you could divide by that, so this becomes a 1, and then you can use that 1 to cancel out this negative 2. So what I mean by that is you could say this is 1, and then you could divide by minus 3i. Oops. You know, you just row reduce like you normally would. And then you can simplify this if you'd like, and then you can add, you know, 2 copies of row 1 to row 2 to get a 0 here. So is this making sense so far?
Yeah, I see.
So this becomes some number, and you get some in here, and you just keep going. It's just a little messier because it involves like dividing by complex numbers.
Right. So like the answer in the textbook, it kind of just assumes without row reducing that negative 2x1 equals negative 1 plus 3i times x2.
Yeah, so what they're doing is this matrix over here that we get, this matrix, you know, we know that there's something in its null space. So we know that there's 2 eigenvalues, 2 plus or minus 3i. So we know that the eigenspaces, each one-dimensional. So this matrix has one-dimensional null space. This 2 by 2 matrix has a one-dimensional null space, which means that these columns are linearly independent. It means that, you know, or the rows are linearly independent. It means that these are just multiples of each other. These rows are just multiples of each other. They're kind of, if you were to write this as a linear system, they would be a redundant linear system. These 2 equations would be exactly the same.
Wait, how do we know the eigenspaces are one-dimensional?
Because you have 2 distinct eigenvalues. And so each eigenvalue has at least, you know, a one-dimensional eigenspace, and it can't be bigger since this is a 2 by 2 matrix.
Oh, okay, I see.
Yeah, and so you know that, like, if I were to write this as a linear system, for example, even though they look very different, these are actually the same linear system. These are the same. They're just multiples of each other. And so since they're the same, you can just pick any one of them and you get a free variable and a pivot variable. And so this implies that X, you can just pick one of them. For example, I can look at the second one, because that seems like a nice one. I can make this one, there's some arbitrariness in this. I can pick this to be 1, or even I can pick, and then I can just figure out what this needs to be so that I can solve for x1 here. So it's -1 plus 3i over -2.
Okay, I see. So is it okay to always, instead of row reducing, just pick either row because we know that they're linearly dependent?
Yeah, if you have some example like this with a 2 by 2 matrix, you know that there's going to be, they're going to be linearly dependent if you did everything correctly. If you solved for your eigenvalues correctly, then you know that there's a one-dimensional eigenspace, so you know these are just the same. So you can just, if you don't want to row reduce, you can just choose this as a solution. The thing is, there's also other solutions you could choose, right? You could have chosen, this, for example, -1 minus 3i over -5. This would also be.
Oh, but this would only work for 2 by 2 matrices, right?
Yeah, if you have 3 by 3 matrices, and maybe your eigenspace is one-dimensional, then you need to do some row reduction first.
Okay, to see, I guess, or I guess you'd have to just row reduce the whole thing to find the answer.
Yeah, and it's just a little more annoying with complex numbers because you have to divide by complex numbers, but it's not too hard.
Okay, I see. Got it. Thank you.
Mm-hmm.
Wait, can I ask about number 25?
Sure.
I still don't really understand the proof. I've been like trying to look over it and I still don't get it
25.
for 5.5.
So you have A is real, n by n. And x is a vector in Cn. And you want to show the real part of AX and the imaginary part. Okay, so oftentimes with things like this, you can actually just first do it with just normal real numbers and complex numbers instead of vectors and matrices. And it'll be basically the same proof. So what if we do this small case where A, instead of a real n by n matrix, let's do a real number. And let's say X is a complex number. Then what if we try to do the same thing? So then does it make sense that the real part of AX equals the real part of A times the real part of X? Does this make sense to you?
Yeah.
Yeah, just because A is real and X is complex. So maybe X looks like U plus VI, and A, well, doesn't have any complex part of it. It's just A plus 0I, maybe. So AX, the real part of this, is the real part of, you can just multiply them, and you just get A times the real part of X. Right? You just get this U times A. And that's exactly the same thing that's going on with matrices. Right? So now maybe your matrix is A, maybe X is over here. This is real. This is complex. So maybe we can split up X into its real and imaginary parts. is A, and X is maybe some U plus VI. This is X. This is still real, just a real matrix. Then the real part of this it's just going to be, if you multiply these out, you get A times U plus A times V with an I. So it kind of splits up naturally into real and imaginary parts. It equals A U. A times the real part of X.
But you couldn't say this if A wasn't real, right?
Right. You couldn't say this if A wasn't real. In the same way you couldn't do it if for numbers, right? If this was not real, if this had like a B, maybe it had like not an imaginary part, then AX is not this is not true anymore. You get A plus BI times U plus VI, and now you have not just AU, but you also have this like minus BV, this cross term. So it doesn't work if A is not real.
Okay. Thank you.
Mm-hmm.